pleasure to have our speaker, Eric Xu, speaking us from University of San Diego, California, University of California, San Diego. So Xiaohua spent his undergraduate at the USDC in China, and then spent the rest of the time for his PhD and then a postdoc researcher until now at the Scripps Institution of Oceanography at the UC San Diego. So today he's going to talk about his relatively recent work, the work that I've done after his PhD, about the progress, particular on the Ridgecrest earthquakes. That there are many associated works that in the community, people have published or are on the way of publishing about this earthquake. So Xiaohua is going to share with us about his perspective on it. So with that, I will give it the rest time to Xiaohua.
Okay, thanks, Zhangzhou. Hi everyone, I'm Xu Xiaohua from UC San Diego. So today I'll be talking about the surface fractures near the Ridgecrest area. Here are like a few, jumping everywhere. So here are a few colleagues that collaborated with us during this study. Before we get into today's talk, here is a short outline. Since I was told that most of the audience today does not have much background in INSAR or geodesy, I'll make a brief introduction to what is INSAR at the very beginning and why we recommend it for many shallow crust processes. Then we'll go through some of the tectonic settings, the observations we made, our modeling, analysis, and some interpretation. And in the end, I'll wrap up with some conclusions. Before we talk about INSAR, I would like to make a short introduction to GNSS, as they belong to the same category when it comes to geophysics, that is space geodesy. I guess most of you guys are familiar with GNSS one way or another. Generally, it is constructed with a constellation of satellites that have known orbits. So each satellite transmits electromagnetic signal that contains the time information, and then the station on the ground records the time information and the arrival time. You'll be able to get the distance between the station and the satellite. Then with multiple satellites going in this constellation, one could derive the precise position and velocity for that station. Largely, these space geodetic satellites have the following features. First is you have satellites with known precise orbits. In other words, you know the location of the satellite. Second is the satellite could measure distance or other similar parameters between the satellite and your target on the ground. When it comes to INSAR, it follows a similar concept. First, you have satellite with known orbits. The second is the satellite could measure distance between the satellite and your ground target. However, for INSAR satellites, it could only measure one component of this what we call position or velocity, that is along the direction between the satellite and the target on the ground. In this case, a SAR satellite sends pulses of electromagnetic signal and record returned echoes. The radar echoes contain two parts of information, the amplitude and phase. The amplitude tells how reflective the ground target is, while the phase tells information of distance, even though it's in a wrapped format. But if you only measure once, you find that the phase map is largely like noise. This is because the radar wavelengths or radar bands is largely a few centimeters to tens of centimeters, but the topography or the ground scattering properties change very fast in space, much faster than radar wavelengths per pixel. And if you differentiate two of the measurement, for example, over here, you get coherent fringes. The reason is that even though topography or scattering property changes very fast with space, but the change of topography or deformation changes actually pretty slow with space. That's why you're able to see these fringes. That's largely how INSAR works. Of course, you need to correct for Earth's curvature, topography, or sometimes atmospheric noise to really let the deformation show up. Okay, one more slide before we really go to today's topic. I would like to emphasize just a tiny bit on why INSAR is the way to go for future geophysical studies. Compared to GNSS, the cost for INSAR is relatively low. Though the temporal sampling is not very high, usually like a week or 2 weeks, but in terms of understanding most geological or anthropogenic processes, it is fairly fine, as most of them took place in a very slow manner. INSAR techniques are under very fast development these years, primarily because of the open data policy from ESA. So they have launched the Sentinel-1A and 1B, and all the data from those two satellites are free and open. For data from other agencies like JAXA, ALOS-1, ALOS-2, you can also get the data by writing proposals. And in a few years' time, the NISAR mission will get launched. Is by NASA and Israel, which is a space agency in India. They also have committed that the data will be free and open. So on the other hand, like other than these free and open data, the scientific community has started to realize that this is a very good method that could be applied to a number of research fields. In the 2017 NASA Decadal Survey, they also recommended that INSAR should be the primary tool for studying surface deformation and dynamics. So the next 10 years is probably the golden age of INSAR. One of our job is to develop open source software to minimize the prerequisites for anyone to use this amazing technique, not just for geophysics, but also for environmental science or urban infrastructure monitoring and so on and so on. So you are welcome to like come and explore with this amazing data set. Okay, back to our topic. Here's a tectonic map for the region I'll be talking about today. It is largely located near the Mojave Desert, in between the northern part, which is the Walker-Lynn Belt, and also the southern part, which is the Eastern California Shear Zone. This mini-map sort of tells you where this area is. That is the Garlock Fault, and this is a San Andreas Fault. These white segments denotes historic events, like this one is the Owens Valley earthquake in the 1872, and also the 1992 Landers, 1999 Hector. This is the earthquake rupture region, and to the north of that, that's the coastal geothermal field. You can sort of tell that both of these earthquakes stopped at there because of the very high geotherms. So here are some previous studies over this region. This paper by Amos et al. In 2013 mapped the surface fault near this region, which is really close to the rupture area. It's called Little Lake Fault Zone. And what they found is that the slip rate over the past 200 kiloyears is about 0.6 to 1.3 millimeter per year. Well, an earlier INSAR study by this Peltzer et al. In 2001 found actually the slip rate might be 7 ± 3 millimeter per year. Well, these two might be measuring different things. Apparently the second is slightly larger. There are like arguments, for example, like the strain accumulation might be elevated after the 1992 Landers, but that's yet to be debated. Anyway, but just from these two analyses, you can sort of tell that this area is actually, the accumulation of stress is essentially pretty low. Then there comes the earthquake. Like Ridgecrest Earthquake took place on July the 5th, 2019, and actually 36 hours prior, you have the magnitude 6.4 foreshock. After the earthquake, we quickly assembled a team. We had a few email changes, and then we went out to the field. We're really serious about the research. You can sort of tell from these images. The main rupture is a right lateral rupture, which is the picture on the right. And the foreshock is actually, the 6.4 is a left lateral rupture. So after we get back from the field, we quickly process the INSAR acquisitions from the Sentinel-1 satellites. The data is from the European Space Agency. It is very well mapped by the two local direction. You can sort of tell from the regional map over here on the right. We have data, observations from the descending track, also from the ascending track. This red boxes actually denotes the area presented over here for these two interferograms on the left. After you get the interferogram, once you get the interferogram, you could perform a procedure called phase unwrapping. This is a procedure that could connect those wrapped fringes together to produce continuous or not continuous deformation field. Some of this discontinuity you see in the map is actually from the rupture, which could be real, but some of them could be artificial, for example, here, like in this pocket area. That is because the phase as part of a complex number, the field of complex numbers sometimes is not really analytical. You would have like what we call residues in the map, and you would have more residues when it comes close to the fault rupture. So that's why you would see some of these artifacts over here near the rupture. And the map on the left is from the descending track. The satellite flies largely from northeast to southwest with looking towards its right. The positive colors means the ground is moving relatively towards the satellite. In other words, like this way. The blue color means it's getting away from the satellite. So for the main rupture, you can sort of tell that it is largely a right lateral rupture. And for the foreshock, it's largely left lateral. You can sort of derive the same kind of sense from the other map. Like we said, because phase unwrapping is going to create like artificial discontinuities. Here, what we recommend when it comes to finding small details in the map is this technique called phase gradient mapping. Essentially, the phase is a measurement of distance change, right? So the gradient of that is essentially measuring strain change. There are a couple of advantages and disadvantages for this technique. The best part about this technique is because you can essentially perform the gradient on the real and imaginary parts of this radar echo, you don't really need to unwrap the phase to get the phase gradient. Also, it is able to bring up a lot of details in the map. And also it can be directly stacked because you don't need to unwrap the phase. The disadvantage is that when you're taking derivatives, it's actually magnifying noise. And because it is magnifying noise, it's strongly affected by decorrelation. In other words, any part of the incoherent images is gonna get, it's gonna get worse. So in order to suppress noise, we're actually combining like these two filters together when it comes to taking derivative. Actually, when you're taking derivative, you're also smoothing the data with a Gaussian filter. Here's getting a little bit technical. I promise this is the last slide of technical stuff. It's that when you're taking this phase gradient map, you shouldn't do any multi-looking. And multi-looking has been sort of like built in INSAR processing for many years. And contradictory to that, the reason we don't want to use multi-look is because if you look at these two kinds of filter in the spectral domain, you'll find the Gaussian filter doesn't have a leakage problem when it comes to high wave number or high frequency, but the boxcar filter is going to give you a spectral leakage. This kind of leakage is going to get worse when you are sampling your data at the same size of your boxcar filter, which is what people usually do for multi-looking. When you directly look at the phase, it may not show you like a significant difference, but when you look at the phase gradient map, you can sort of tell that the top map actually gives much less noise. And essentially when it goes into the second map here, a lot of small features are largely just gone. But directly looking at the map, you can sort of tell that even with the smoothness we added from the Gaussian filter, the data may not be that good, right? But after like 20 years, now we have Sentinel. I think I don't have to say anything to convince you that the current data is much better than before. So what are we seeing here? I'm not sure the image resolution is good enough when things goes online, but can you see these lines like over here? Like essentially, like for these kind of lines, when you see a strong contrast, it's actually meaning strain localization. In other words, that part has a relatively stronger deformation than other areas. So another question would be like, for these lines you see, they are pretty much everywhere in this map. So what are they really doing? Or in other words, what really happened to those, what we call surface fractures during the earthquake? To really understand that, you have to go back and look at the phase. And luckily, we have two look directions. for this event. You have the ascending orbit that largely goes from south to north. You have descending orbit that goes largely from north to south. And because the local angle is largely symmetric for this area, you can essentially do a decomposition to extract sort of independent maps. One of them is the east component. The other one is vertical with a little bit north-south component combined. Here are the two maps. Oops. Note here that the positive on these two maps means east. The other one positive means upward motion or south motion. Also, these are very straight lines. You see the map and the previous phase gradient map. For example, here is an example. You can sort of tell that there are like red colors on top of blue colors, right? So red colors means it's moving to the east. Blue colors means it's moving to the west. So this one is actually deforming right laterally. Things are a little bit messy when you are still looking at this kind of scale. So let's zoom into one of the place to the south over here. So this thick line, colored line over here is actually the magnitude 6.4 rupture. You have blue on top of red. So this is largely a left lateral rupture. But if you look at other like surface fractures, you'll find that most of these are actually deformed right laterally, right? Things are getting interesting. And along with these fractures that goes backward, there are some level of subsidence associated with each of them. So why did they actually go backward? Normally, if an earthquake happens, it usually deforms or goes along in the direction of the tectonic stress. For example, here surrounding the Ridgecrest region, the inferred SH max or the maximum compressional direction is north-south. So in other words, if the an earthquake that goes largely along the direction of the main rupture, it should be right lateral. And if it goes along the foreshock, it should be left lateral. Here we define for these fractures, if the measured deformation goes in the expected direction from the background tectonic stress, we call them prograde fractures. If they go to the opposite direction, we call them retrograde fractures. If you map all the surface fractures on the surface, here's a map that shows what it looked like. At the very first look, there are like a few places you would notice that have this kind of transition, right? So these two are actually essentially going backwards, but when it comes to a little bit further area, these are becoming prograde. And also for these area, you can see blocks of prograding and retrograding fractures. So normally, when you are thinking of these fractures, we don't really believe that the tectonic stress could drive things going backward, right? So you need another source. And the biggest source for this area, of course, would be from the Ridgecrest earthquake. And to understand the stress release from the earthquake, you need a source model. So we built a source model. So the data we used for that source model is Sentinel-1 data, ALOS-2, and also the along-track interferometry from ALOS-2, three-component Gnss displacement. We also have on-fault offset estimate from optical imagery. The method is briefly described in this paper back in 2016. And here is a source model. So you know that I'm telling this kind of storyline that works best in logic manner, but actually in the real world, this is the thing that comes out first. We have this model pretty much like 1 week after the earthquake. I guess what I mean is that you may not necessarily follow the logic when you are really doing research sometimes, but never mind. We did modify a bit to split the two events from using the Gnss data. So we have Green's function for each of them. And the resulting shallow slip deficit for this event is about 29%. I'm not going to get into details right now for the shallow slip deficit, but do remember that we get this number, and later on we're going to come back. So after we get the source model, we can essentially compute stress along any given direction at any given depth. What are shown here are two examples: the stress with friction coefficient assumed to be 0.4, and along the main rupture, this is the right map, and also along the foreshock direction. After you get this ability to compute stress, you can essentially play with some parameters. Then we use this stress results to make more analysis. The first one is this friction analysis. Note that all our observations are made at surface, and due to its scale or pattern, these deformation could not be from very deep. So we kind of assumed about 10 gigapascal shear modulus and also 0.25 Poisson's ratio to compute column stress along the direction of each of these small segments of the fractures. Then we try to determine whether they match the observation from the INSAR data. If they do, we mark them with colored segments. If they don't, they are colored as black. The number of matching segments is the rating that we're using here. You can sort of tell. And from this kind of rating, it kind of feels like seems the analysis kind of prefer a very low friction, but does that really indicate the area has a very low friction coefficient? Actually, you can't really derive that like a conclusion. That is because if you think about the analysis we're doing here, it is the shear stress that actually determines which direction the fault is going to go. The normal stress combined with the friction coefficient can only allow that to happen or prohibit that to happen. In other words, that's why this small coefficient is actually preferred by this analysis. In other words, what I'm trying to say here is that the direction these fractures are going can largely be predicted by the shear stress. Another analysis we did is about the background tectonic stress. We only largely know its direction, which is north-south compression, but we don't know what number it is. And since normal stress does not play a significant role, here we're going to add only just the deviatory part of the stress. So we assumed north-south compression with equal east-west extension. The resulting number is around like 0.4 megapascal, as you can sort of tell from this curve. So I don't have enough time to really go into details of what this number means. You can sort of consider it as a stress indicator. Of course, it's only for the shallow surface. Once it goes to the deeper depth, of course, the stress is going to be much larger. And from this three plots, you can sort of tell when the stress number, added stress number is low, this part of transition is going to fail, right? And when you have a larger stress than 0.4 megapascal, this southern part is going to fail. So I guess we could sort of conclude that the Coulomb stress is able, or stress, shear stress is able to predict what direction it is going. The remaining question is, what mechanism are these shallow fractures? If you look at this map, here's the east-west map of the same area we already showed, and also the south-north and up-down. Seemingly, there are two problems with these observations. The first is that when you take a profile along these fractures, you'll find that the step crossing each of these fractures is not very sharp. In other words, if you think about the frictional slip scenario, that indicated the slip didn't really go up to surface. It's a little bit hard to explain like why it did not go up to the surface. The second is associated with these fractures, they are also like downward motions. It's unlikely that when the fault is frictionally sliding, it's also collapsing and falling at the same time. But in fact, other than frictional slip, we also have another like mechanism. The alternative explanation is called compliant fault deformation. So compared to what frictional slip or frictional sliding predicts, where the fault under like excessive stress will slide with the fault plane breaks in the middle, the compliant fault deformation scenario does not require the fault to break. In other words, this is a scenario where your fault is surrounded by a fault damage zone, where the shear modulus is actually smaller than the surrounding hosting crust. And then under the stress perturbation, the part of the weaker material surrounding the fault will deform more. In other words, the strain is going to get localized surrounding the fault. So that's a compliant fault deformation. Actually, we're not the first to observe this. Back in 2002, Fialco et al. Already discovered this phenomenon for the Hector Mine earthquake. Here are like a few observations from their earlier papers. These two faults called Calico and Rodeman actually exhibit similar behavior as we sort of saw for those retrograding fractures. You could sort of tell directly from the phase gradient map that these motion typically have like a wider deformation zone than the prograding fractures, right? So could it be the case for most of these observed fractures? Could all these fractures be compliant fault deformation? Before we really get into that, here's another issue that needs to be considered. Just for compliant fault deformation, there are actually two types of mechanisms. One is just like what we talked about, the fault will respond, the stress perturbation as a like sort of three-layered like model. The other one actually is when, because people believe that when the seismic wave passes by, it potentially will create more damage to the existing fault damage zone. Thus, the shear modulus might drop. And that is actually observed by this Vidali and Lee paper back in 2003 for the fault of Landers rupture near the Hector Mine earthquake. Once the shear modulus drop, given the same scenario of tectonic stress, then the strain will be more localized in the fault around the fault damage zone. In other words, you'll see similar things that happen like to what we observed as a compliant fault deformation. However, this type of mechanism could hardly generate deformation that goes backward because everything is still driven by tectonic stress. So that's one part of the like this kind of theory when it comes to retrograde fractures. Also, since our observations come from sources that are quite shallow, you wouldn't expect the stress to be very strong. As we are more interested in the backward motion of these fractures, we will sort of remain for the first mechanism of compliant fault deformation. And to understand what really happened to these fractures, we took profiles along every single surface fracture for this area. We took the profiles and stacked them together, and then we measure the deformation width across the fault and also the amplitude. Then with assumed parameters like the surrounding shear modulus and also the computed shear stress, you can actually derive a parameter called the shear modulus contrast. If you do this kind of analysis for like all of the fractures, then you can actually plot the histogram of these parameters. What is plotted here are histograms of deformation width, the displacement amplitude, and also the shear modulus contrast. So the different colors here, the yellow colors mean it's done for all the surface fractures. The magenta one is for the prograding fractures, and the light blue is for retrograde fractures. So for the displacement, they do not show a statistical difference, but the retrograding fracture seems to generate systematically wider deformation, and thus created a shear modulus ratio that's physically would make more sense, which is sort of between 0.4 and 0.8, if you can find it over here. For frictional slip, the deformation, this D over W, deformation over width term, will be really sharp. Will be really large because usually the frictional slip is really sharp at surface. And thus, when you take that into this formula, it's going to give you unreasonably low shear modulus contrast. The reason that we say this 0.4 to 0.8 is sort of in the reasonable region is from seismic tomography. So this is a study by Alam and Benzaia in 2012. So what they found is that surrounding the San Andres, this fault and the San Jacinto fault, seems the shear wave velocity have up to like 40% a reduction in the upper top 5 kilometer depth. Of course, this kind of blob-like or halo-like feature is telling you the resolution is not very good, but I sort of believe their numbers. And if you take in this 40% reduction number into this computation, you'll find, for example, a 0.6 to 0.9 shear wave velocity ratio is going to result a 0.4 to 0.8 shear modulus contrast. That's why we say that seems the retrograding ones are producing like reasonably like fault damage zone, this kind of theory. So it seems that we could safely say that the prograding fractures are likely to be frictional slip, while the retrograding fractures are likely to be compliant fault deformation. But observation is observation. We need a model to explain what is observed. And here is a conceptual model. So we made this model that is called the critically stressed fault. Initially, everything is just reset. You can sort of see from this plot. For example, like after a big earthquake, everything's reset. Then just with tectonic loading, the fault will get into a status where it is on the verge or breaking into a frictional slip. And with a tiny bit of extra stress, it's gonna evolve into frictional slip, just like when it's going from 1 to 2, and then to this frictional slip. I guess the key here is that this kind of frictional slip does not really release all the accumulated stress. In other words, it releases part of that and then turn the status back to what we call critically stressed status. In other words, naturally, just from tectonic loading, you would have the fault evolving from 1 to 2 to 3 and then back to 1. So under this scenario, when there is extra stress imposed to this fault from surrounding earthquakes, you see that if the stress that goes along the direction of the tectonic stress, it's likely just to follow what we talked about, just like frictional slip. However, if the stress from the earthquake actually goes against the direction of the prevailing tectonic stress, it's actually going to bring the fault away from failure. In other words, the fault's going to maintain as a continuum and respond as a compliant fault deformation. And because the fault is a continuum, it is also able to sort of respond to the compression or extension for the area. That's why we see those kind of subsidence from these faults. Here are a few more examples. For example, we saw this transition at the northern part of the epicentral area. Then if you go to the nearest surface fracture, it's a little bit messy here, but you can sort of tell that along this fault line, things are actually going left lateral. And along with that fault line, you can also see quite strong subsidence. And when you go to the furthest fracture here, you see that everything is pretty much horizontal and you don't see much like vertical deformation. And the horizontal motion actually tells you it's a right lateral, sort of like a frictional slip. The real interesting one is actually the one in the middle. It sort of lies in the transition zone, where you have the stress sort of transiting from promoting a left lateral motion to promoting a right lateral motion. That's why you don't see much of a deformation until it goes to the right end, where it's further into the right lateral promoting part. And you do see subsidence associated with the fault until it goes all the way to the right. So this essentially actually is a really good proof of our theory. There are like some exceptions of observations. In the like earlier papers, I think they did not try to make a very strong link to stress change from the earthquake, primarily because the shear stress where it is the strongest, these two faults actually goes forward. In other words, the shear stress is saying that you should go into the other direction against the prevailing tectonic stress, but actually they didn't. This might be a really unique case. In other words, if we think about the critically stressed status, actually it's controlled by a lot of parameters like the normal stress, like the friction of the fault, or maybe even the coherence of the fault materials. In this case of the Hector Mine earthquake, this is actually located at the area, if you're familiar with the strike slip events, this is actually at the extensional quadrant of a strike slip fault. In other words, the normal stress is going to drop by a lot. And when the normal stress drops by a lot, it's actually it's going to lower the status, stress status of that model. That's why this fault, even though it's affected by backward like shear stress, it's still like go forward. This is because the shear stress released from the earthquake is not larger than the tectonic stress, which kind of makes sense. And there's another like concept over here that is maybe these faults actually deformed in the mechanism of the second like theory of the compliant fault deformation, which the damage is getting like stronger, thus the strain gets more localized from the tectonic stress. But actually there is a dilemma for this kind of theory is essentially you can explain the motion that way, but the thing is that when that happens, the deformation width should be largely just the fault damage zone width, right? These two faults at the northern part actually has like 1 to 2 kilometer wide deformation zone, but these two are actually pretty narrow. So it's a little bit hard to explain why the fault damage zone actually changes its width along the fault line. So I guess that's most part of the model and theory. And now we're trying to get some implications out of this study. The first and the foremost is that we found a lot of more faults. Essentially, frictional slip in its mechanism could be like new ground cracks or shallow fault creep. There is a possibility that they are not really associated with any faults. But the compliant fault deformation, you have to have a pre-existing fault for that. In other words, all those that goes backward are essentially faults that were never mapped before. This techniques is giving us essentially a new tool to map fault from space. You don't really have to go out of the field. You don't have to really see a geomorphology like evidences to determine that there should be a fault over here. This is actually quite useful for places where the strain rate is really low and most of the faults are bland. But on the other hand, this technique is actually quite picky. It could only be applied to places where very good coherence exists, for example, like in the Ridgecrest area in California. And this is not possible without the Sentinel-1 satellites. Also, we kind of believe that these type of fractures may exist in many other like diffuse strike slip systems, like the recent magnitude 6.5 Monte Cristo Range earthquake in the Walker Lane belt, and also the 2017 Iran-Iraq earthquake. We really should dig into this and check whether they are providing any new insights. There are some like interesting characteristics you can sort of derive from these observations as well. First is that these faults must be very young. To be more exact, I think I should call it immature. There is this scaling law by Coe and Schultz in 1992, where, for example, for these faults that we observed, most of them are like from a few kilometers to like tens of kilometers long. So from their scaling law, these faults should have cumulative. I mean, the historic slip for these faults might be just from 10 meters to 100 meters. Also, Savage and Brodsky in 2011, they find this relation between the total fault displacement and fault damage zone thickness. In other words, if you look into this map, you'll see that maybe like around 100 meters of total displacement will give you about like 100 meter wide damage zone. So if these two relations are accurate, then essentially all these small segments we see over in this area, they are associated with very young faults. Another question is like, how deep do these faults go? Here's a simulation study by Ampuro and Mall in 2017, where they produced this relation between fault damage zone width and the seismogenic depth. A smaller seismogenic depth will produce a narrower fault damage zone. So based on this relation, we would expect that all the discovered fault here should be largely like less than 5 kilometers deep. One more aspect you could think of is that these faults, though narrower than the previously observed Calico and Rodman fault near the Hector Mine earthquake, they did not provide a dramatically larger or smaller shear modulus reduction. Like the numbers you can derive for these faults are still like 0.4 to 0.8. So this really implies that the evolution of a fault may not be really producing more damage inside the fault damage zone, but rather just growing its width or growing its size. All of these could only be addressed with much more similar type of observations. Finally, I would like to talk a little bit about shallow slip deficit. I got involved into this problem at my like early stage of PhD. So before we get into the implications, I'll explain a little bit what the shallow slip deficit is. So you have like nice observations of deformation from the INSAR for a particular earthquake. Then using this displacement observations, you can derive from a finite fault solution to see like what really happened during the rupture. And for the large strike slip earthquakes, if you integrate all the strike slip along the strike and plot it versus depths, you see a map sort of look like that. So the maximum deformation happened at a certain, maximum slip happened at a certain depths, with it's tapered towards the deeper depths and also to the surface. The damping you see when it goes to the deeper depths is not a big problem because generally that's where the driving forces come from. But the shallow part, where we call the shallow slip deficit, is kind of a problem. Because when you do this kind of analysis for many large strike slip events, they all follow like similar behavior, where you have a maximum slip at a certain depth, and the shallow part has a missing slip. And the problem is that these shallow deficits kind of too big. Like back in 2016, we found that this extra large shallow deficit might be from lack of data near the fault. So after some refinement, these numbers are getting smaller. If you're interested in this problem, you can read these papers. It's a really interesting problem. And back to Ridgecrest, you are actually getting a number that is about 29%, which is essentially larger than any of the strike slip events that happened in Southern California or Baja California. Usually when people try to explain this remaining shallow deficit, there are like two major hypotheses. Like one is like the shallow slip occurs on the shallow fault at other times in the earthquake cycle. The other one is shallow slip is taken on other distributed structures. The hypothesis one has a lot of like supporting like ideas or studies. Like even though some people talk about like plastic strain or distributed faulting, but most of them are within like 1 or 2 kilometers of the fault, which actually belongs to category 1. And what is observed here from our study is a direct support of hypothesis 2. Where when you have so many shallow structures that could be like, I mean, that could be happening like earthquakes, it's hard to like say this is not an evidence for hypothesis 2. But of course, finding supporting like argument for one does not deny the existence of the other. Also, we did summarize all the deformation associated with these fractures, and their total is actually less than 4% for both prograding and retrograding fractures. I guess what I'm trying to say here is that they are not really taking account for the shallow slip deficit co-seismically. Based on the conceptual model, these faults like surrounding the major rupture, they should be releasing strain aseismically over the interseismic period, or they should be taking turns to produce similar smaller events. However, this area is very low strain rate. We did stack a bunch of phase gradient maps over this region, but we did not find any strain localization. So based on that, we kind of think it might be this second. In other words, these small structures might be taking turns to have an earthquake to account for the shallow slip deficit. Okay, here is the conclusions. I guess most of these I already talked about them. Like we found a lot of unmapped faults, more with the relation, like if you think about the relation between the fault damage, fault length, displacement that we discussed, this actually provides us a new way of mapping faults. You don't really need to go out to the field. Like some of these are actually going backwards, and the mechanism for prograding and retrograding fractures are quite different. The prograding ones are frictional slip, and retrograding ones are compliant fault deformation. And these faults we documented are actually in situ records that even for very immature faults, they also have well-established fault damage zone. And these fractures might account for the larger shallow slip deficit that we saw for the 2019 Ridgecrest earthquakes. I guess that's all. Thanks, everyone. I'm happy to take any questions.
Hey, Xiaohua, thank you very much for your talk. And now it's time for a question from the audience. So if you ask a question, please let us know your name and your institution. Actually, I have two simple questions, quick questions. Could you go to your final slide? I'm just curious about that. Do we have any other this premature or immature, or like a premature earthquakes that happened before in the history that could cause to the magnitude of maybe more than magnitude of 7?
You mean like a big earthquake that happened on an immature fault?
Yes. What is the biggest one from the immature fault?
I don't think we have a really good definition, like because most of these that we observed, they already have some level of historic events. Even for the Ridgecrest, where the fault mapping isn't done very well, like after the earthquake, after they did a careful like mapping, they kind of believe at least 50% of the segments have records of historic events. And when it comes to like how mature they are, I think they are yet to be debated. It's not really a determined thing yet. The largest I can think of for these earthquakes, I don't know, something like 7 maybe. I don't have an exact number in my mind.
Okay, but so far as for all the earthquakes that are more than magnitude 8, none of them that belong to this category. Is that right?
I think in order for you to have an 8 earthquake, it's more likely to be just a thrust event. Like for strike slip event, it's really hard to have a magnitude 8.
Okay, right. So Ridgecrest is pretty much hit almost the upper limit of this type of earthquake.
Yeah, maybe. Like most of the largest strike slip events are like 7-ish, less than 8.
Okay. Okay, that's interesting. Another thing
well,
that
I'm only saying the shallow ones. Like the deeper ones could be different, you know. Like because when you say strike slip or thrust, like what I'm saying here is just for the shallower earthquakes. Once it goes to the deeper, it's a different category, I think.
Okay, I see. But when you mean deep, you mean
like hundreds of kilometers.
Oh, okay. You mean the super deep?
Yeah, the really deep earthquakes. Yeah.
Okay. All the way to the maybe transition zone or even lower metal. Okay, that's of course another story. Okay, could you turn back to a couple of slices? I forgot which one.
You mean like what?
Yeah. Okay. Just like this one. Actually, like a simple question. No, the next one, because there are normally 3 seconds delay.
This one.
Going forward, I think maybe number 35.
Okay.
Okay, I have a relatively simple. This is 35.
Oh, 35. I'm sorry, because the number here is not the same as the one that shows up in the slides.
Okay. Yeah. Okay. So for this one, actually, one thing that I think probably is a very easy question for you, but sometimes like I'm not so clear. That here you show the vertical axis as a depth. So from the shallow ones, I could tell that, like say, like say this type of the slip, that how much that has moved, that could be measured. So for the deeper ones, like I said, 10 kilometers or 16 kilometers. So how does this horizontal values that come out? Was it coming from seismology, or is it any other type of integration you have made for your INSAR data?
You mean like how does these numbers come from?
Yeah. How does this number come out?
They are from the slip model, like directly. If you build a slip model and then you do this kind of integration and just plot it versus depth, that's where the curve comes from. But the thing is that when it's at very shallow depths, it's easier for us to constrain because most of our observations are at shallow surface. Once you go deeper, the resolution is gonna get worse and worse, especially for geodetic data.
Okay, so for this 34, so for the 35, so the points that are labeled here, like the different symbols, like the diamond, triangles, or squares. So those are actually the model points that come out from the previous. Okay. So that almost like that means like some of the transition, I say the key points in those model, because I think that's each model should be a continuous model, although it divides into many smaller boxes.
Yeah, this is a sum of everything.
Okay.
Yeah, it's not with respect to each of the fault plane. Like each of them could be like different. This is just a total effect.
Okay, thanks. Okay, do you have any other questions from the audience? Feel free to open your mic.
Hi, Xiaohua. I'm Qinben from Beijing University. Could you hear me?
Yeah, I can hear you.
So I wonder, how do you find this shallow sleep, or this through the satellite pictures, or how many pictures are there, or I mean, yeah, do you just look at them and find this this thing?
You mean the surface fractures?
Yeah.
Let me go back to the slide where like for these ones.
Yeah.
Or that one. So the phase, in fact, there are like two aspects of finding these. Like I said, that the phase unwrapping sometimes is going to give you artificial discontinuity that sort of look like a surface fracture, right? So directly from the phase map, you can't really get a good hint of whether that is real or it is just artificial, like from the phase unwrapping. So in other words, to really determine like whether it's a real or not a surface fracture, we're using the phase gradient map. Of course, this map is being stacked. Like we have about like roughly like maybe like 6 or 5 images for the descending track, and maybe like 20-ish for the ascending track. And after stacking these kind of like short wavelength noise is largely from the atmosphere, is gonna be gone. So that's why this one looks much better than the other one. But that's also because the earlier data, because the bad quality, bad control of the orbits, you don't have that many images to be stacked with. And after you know like where location you should be looking at, then you get into this decomposed map from the INSAR phase, and then try to determine like, say, oh, this actually is a fracture that deformed during the earthquake. So this is how we determine like that it's actually a combined contribution from the phase gradient map and also the decomposed phase map.
Yeah, thank you. And this is happened only maybe half a year or 1 year to?
No, it actually, it's pretty quick. Like pretty much like a month after the earthquake, we already got this.
Okay.
And the earthquake took place at early July, and we got this results pretty much like 1 month later. And then we presented it like at SCAC like 1 month later. So,
okay, got it. Thank you.
Okay, I have another question. That do you see, maybe this is not directly relevant to your talk, that do you see that machine learning will play a role in the INSAR data
processing? What's your point on it? What you don't think machine learning tool is useful at all?
I think the processing like method is pretty mature now. But in terms of explaining the INSAR data, I think machine learning could like help or contribute. In other words, when you see an interferogram, like processing to this interferogram is really easy. Like most of the processing part is pretty standard now. But explaining, like for example, inside this map, how much of the signal is from the earthquake, and how much is from atmosphere, and how much is from artifact or the design of the satellite. Like in terms of that part, actually, I think machine learning could help a lot.
Okay. Yeah. Yeah,
like
in different fields.
In terms of interpretation, it'll help a lot. But that also requires you to like sort of know what each process is, like before you fill the data in. So
there are research directions people call the interpretable machine learning, that people in particular that want to emphasize that the pros and the cause and consequences, that in particular, like say the contributions of different factors to the final results. Because I've been began to working with another data scientist at the data center here at Zhejiang University, and his group is focusing on that. But it's just a very beginning, so I don't know too much details in that. But I see that there are a lot of people working on this topic. I mean, mathematicians. I bet Marcius at Scripps probably has his tools already. Perhaps he's a mathematician. Okay. With that, it's almost 1 hour. I think we could wrap it up today. And thank you very much, Dr. Xu, for giving the talk. And thanks everybody for participating. And thank you for watching on YouTube or Bilibili if you come here later in our channel. Okay.
All right. Thanks for the invitation.
Okay. Thank you. Have a good day.